Hi, I am Rajiv Shekhar. I am a student of Vellore Institute of Technology. Welcome to my presentation on how quantum computing will transform cybersecurity. Firstly, I will give you a short introduction on quantum mechanics and its principles, because the understanding of quantum mechanics and its principles is a prerequisite for understanding quantum computing. Quantum mechanics is a paradigm of physics that describes the behavior of particles in the smallest scale. It is totally and completely different from the classical physics due to the wave-particle duality of the entities in quantum mechanics. The electron or the photon, which is the basic entity in quantum mechanics, shows the properties of both particle and light. But the entities in classical physics, as I mentioned earlier, are either particle or light. And in order to get into quantum computing, we need to know two of the principles of quantum mechanics. The first one is superposition. In quantum mechanics, superposition refers to the ability of a quantum system to exist in multiple states simultaneously. You can exactly know what state uh, the quantum system is in only by measuring the system. Classical systems usually are in a single definite state, unlike quantum systems. Imagine you have a spinning coin. When it is static or when it has fallen in the ground, it is just only one state, right? It is either heads or tails. But what happens when it's spinning? It's not just heads or tails. It is in a state where it could be both heads and tails at the same time until it lands and you measure it. Another property of quantum mechanics is entanglement. Entanglement is a quantum phenomena where the states of two or more particles became correlated in such a way that state of one particle depends on the state of the other, regardless of the distance between them. If you measure and collapse one of the entities, then you can surely assert that the other's nature based on the relationship between them. Quantum computing is a cutting edge field of computing that utilizes the principles of quantum mechanics to perform operations on data. As we all know, classical computers use bits as a basic unit of information, which can either be 0 or 1, but cannot be both simultaneously. Quantum computers use qubits or quantum bits. Qubits can represent and store information as both 0 and 1 simultaneously, thanks to a property called superposition, which I defined earlier. You can only find the value of a qubit by measuring and collapsing it. From a cryptographic perspective, assume that the data is in transit as quantum bits. If an eavesdropper tries to get the data by measuring it and collapsing it, then the receiver and the sender will eventually find it out easily and discard the data. Quantum bits are correlated even if they are physically separated. This is the entanglement property which we saw in quantum mechanics. Modifying a qubit or a qubit stream will result in a drastic avalanche effect wherein the data is completely changed. This is the entanglement property because the state of one qubit depends on another. Next, we will see some implications of quantum computing in cybersecurity. So these are some of the implications of QC in cybersecurity. One of the most dreadful use cases of QC is to break public key cryptographic systems like RSA and elliptic curve cryptography. But apart from that, there are also a lot of good implications like random number generation, key distribution, and application of quantum machine learning, which is an interdisciplinary technology which can be used to detect security attacks and handle them in an efficient way. Due to the potential of quantum computing to break existing algorithms like RSA, there is a field of study called post-quantum cryptography, which refers to the evolution of algorithms which is resistant even to quantum attacks. So now let us see how quantum computers are used to break algorithms like RSA. First of all, I would like to give a short introduction about RSA, but I'm not going to go in depth because our topic of discussion is only based on quantum computing. So RSA is a public key cryptographic system, which means that there is a private key for both sender and receiver, and there is a public key. As the name suggests, the public key is almost known to everybody. It is like a global parameter, but the private keys are known only to the parties which own it. The main advantage of RSA is that it relies on the fact that factorization of very large number, which is a product of two already large prime numbers, is computationally impossible. Firstly, we have to understand what is at stake here. Almost $4 trillion worth e-commerce industry uses RSA for security. It has been a powerful algorithm till date because a classical computer will take trillions of years to break the RSA encryption. But a quantum computer will require only 4,000 error-free qubits to solve RSA in seconds. Oh, that is not good. However, this would require close to 1 million of today's noisy and error-prone qubits. Currently, the world's largest quantum computer is currently less than 100 qubits. I can guess what you are thinking now. Because now we have only 100 qubits, it will be a very, very long time before there are 1 million qubits based quantum computers. But that is not true. Because IBM and Google have roadmaps to achieve 1 million qubits just by 2030, which means that in six or less than 6 years, breaking RSA algorithm with the use of quantum computing algorithms like Shor's algorithm, etc., will be quite possible. This means that high confidentiality data like financial data or national security data is at high risk. The solution for this is to adapt post-quantum cryptography, which I defined earlier. It refers to the cryptographic algorithms and protocols specifically designed to be secure against attack by quantum computers. These algorithms aim to provide cryptographic security even in the presence of powerful quantum computers. It ensures long-term protection of sensitive information against quantum attacks. Before getting into public key crypto systems, before getting into uh, post-quantum cryptographic systems, I would like to do a brief summary on what existing algorithms are safe from quantum attacks. Most of the currently existing algorithms cannot survive a quantum attack, but very few cases like AES or the advanced encryption standards are generally considered to be less vulnerable to attacks by quantum computers compared to asymmetric cryptography algorithms like RSA and elliptic curve cryptography. Symmetric cryptography relies on shared secret keys for both encryption and decryption. The security of symmetric encryption depends on the key length and the algorithm's resistance to various attacks, such as brute force attacks. With a sufficiently long key length, symmetric encryption algorithms like AES are believed to remain secure even against quantum attacks. However, it is essential to note that quantum computers could potentially speed up brute force attack or other attacks even against symmetric encryption by exploiting the property called quantum parallelism. This means that while symmetric cryptography may be more resistant to quantum attacks compared to other algorithms, it is still important to consider the potential threats posed by quantum computing advancements. As a result, organizations or other parties which use these symmetric encryption algorithms should take few measures. They can either increase the key length used in symmetric encryption to maintain security against potential future quantum attacks, or they can alternatively use post-quantum cryptographic algorithms designed to resist quantum threats. Another implication in symmetric key cryptography is that quantum key distribution can be used to securely transmit the shared key between the sender and receiver parties. I will talk about quantum key distribution a few minutes later. Existing cryptographic algorithms rely on the difficulty of solving some problem like the integer factorization and discrete logarithm problem. One example for a cryptographic algorithm which relies on these two problems is RSA, as we saw earlier. But the rise in quantum computing algorithms such as Shor's algorithm has made these problems relatively easier to solve, making the cryptographic algorithms which use those problems prone to quantum attacks, like I already mentioned RSA and ECC. So post-quantum cryptographic algorithms try to utilize the fact that some problems are difficult to solve even with the use of powerful quantum computers. One such problem is the lattice problem shown here. The lattice problem can be defined as, given a lattice L in n-dimensional space, the lattice problem asks to find a non-zero vector such that the Euclidean distance of the vector is minimized. It typically involves finding the shortest non-zero vector in a lattice. The difficulty of solving the lattice problem lies in its computational complexity. Even though the problem itself is very easy to define and it may seem easy to solve, finding the shortest vector in a lattice is computationally challenging, especially as the dimensionality of the lattice increases. Even with utilizing the superposition and entanglement property of qubits, it's still a challenge to solve the lattice problem. So one type of post-quantum cryptographic technique is the use of lattice-based algorithms. Here are some of the lattice-based algorithms. The first one is LWE-based cryptography, which is learning with errors. It is a fundamental lattice problem that serves as a basis for many lattice-based cryptographic primitives. It includes a wide range of cryptographic schemes such as encryption, digital signatures, and key exchange protocols. Another lattice-based cryptographic system is the N-True-Encrypt. It is a lattice-based encryption scheme that offers both public key encryption and digital signature functionalities. It is known for its efficiency, and yet it is very simple to implement. The FHE, or the fully homomorphic encryption, it allows computations to be performed on encrypted data even without decrypting first. It is a very unique property of cryptographic algorithm. While it is not exclusively lattice-based, but many FHE schemes rely on lattice-based techniques for their security. Bliss, or bimodal lattice signature scheme, is a lattice-based digital signature scheme that offers strong security and efficient performances. This algorithm can be used for non-repudiation. Another implication of quantum computing in cybersecurity is the use of quantum computing for key distribution. It is a secure way of exchanging cryptographic keys between two parties, typically called Alice and Bob. It uses quantum mechanics to ensure the secrecy of the exchange key. In quantum key distribution, Alice sends individual particles of light to Bob. Assume here that Alice is the sender and Bob is the receiver. These photons, which are sent by Alice, encode the key's bits as qubits. Any attempt to intercept or eavesdrop on these photons would disturb their quantum states, alerting Alice and Bob to the intrusion. After receiving the photons, if they are not attacked by an intruder, Bob measures them using randomly chosen orientations, and Alice and Bob compare their measured choices and discard any measurement that have different orientations. So the remaining matching measurements from both Alice and Bob form the shared key. This key can be used for secured communications later using symmetric cryptographic techniques. Quantum key distribution offers a high level of security as it relies on fundamental principles of quantum mechanics like the superposition and entanglement. Another good implication of quantum computing in cybersecurity is a quantum random number generation. It is a method of generating truly random numbers using quantum mechanics. A quantum device, often based on properties of photons or other quantum particles, is used to generate quantum random numbers. Quantum randomness relies on the fact that the particles in quantum level are inherently uncertain. There are many inherent uncertainty at the quantum level, such as the unpredictable outcomes of quantum measurements. For instance, a QRNG device may measure the polarization of individual photons in random orientations. This will create a random number without any deterministic algorithm. Unlike pseudo-random number generators, which use algorithms to generate sequence of numbers that may appear random to a user, but they are actually deterministic. But quantum random number generator produces numbers that are truly random and unpredictable. Quantum random number generation is a valuable cryptographic and simulation technique, and there are many other applications where the true randomness is essential for security or accuracy. By harnessing the unpredictability of quantum mechanics, quantum random number generation provides a reliable source for randomness for various purposes. Apart from this, there are various other implications of quantum computing in cybersecurity too. One of the major field is an interdisciplinary field between machine learning, artificial intelligence, and quantum computing. It is generally known as quantum machine learning. Usually, there are many machine learning algorithms used in today's world for anomaly detection and intrusion detection. So, quantum machine learning enhances the performance of the existing model which is used for this task. And quantum computing, it is also used to simulate attack and defense in cryptographic systems. There are various other fields which integrate with quantum computing to improve the security. Some of those fields are blockchain and cloud. Thank you. Have a nice day.